Hello, my name is Luke A. Bauer from the University of Florida, and today I am here to present our paper, Towards Realistic Membership Inferences, the Case of Survey Data. Surveys are everywhere and often contain private and sensitive information, and sometimes even the fact that you took part in a survey is private information. The information is usually considered secure, though, because it has been mixed in with many other people's information, so that no one can actually tell who was who, theoretically. This is where membership inference comes in. Membership inference is when an adversary wants to determine if a specific target was part of the dataset that was used to create a survey. Membership inference has been studied before, but mainly within the realm of machine learning. Namely, the adversary wants to determine if a specific target was used to train a machine learning model. This varies from our situation where we're attacking a survey in a number of ways, but most prominently is the fact that we cannot choose queries. We can only use queries that are actually in the target survey itself. In our case, the adversary has access to the target survey, an auxiliary dataset that is separate and distinct but contains information that is statistically similar to the target query database, such as the same database from the year before. In addition, she has access to background information about the target, such as age, address, any attributes that can relate the target to the target survey. She then uses all this information to create probability distributions for each query in the survey. And then for each of these queries, she'll have one distribution that does not contain the target and one distribution that does contain the target. All these distributions are then finally combined to create a final hypothesis of the target is in the dataset or the target is out of the dataset. We have two attacks that actually perform membership inference. The first is a likelihood ratio attack that uses the probability distributions gathered from the auxiliary dataset that we talked about in the last slide and compares it with the survey query result to get the probability of the survey query result under both hypotheses, that the target is out or the target is in. These probabilities are combined to create a likelihood ratio that the target is actually in this query. These likelihood ratios are then multiplied together to get across all queries to get a final likelihood ratio that tells the adversary the likelihood of the target being in the survey or out of the survey. This can then be compared against a threshold to give you a final answer. The other attack we have is a machine learning attack that uses a logistic regression model to determine if the target is in the dataset or not. It is trained using sample queries generated from the auxiliary dataset, some of which contain the target and some of which do not contain the target. This is then given to the model, which outputs whether the target is in or the target is out. This can then just be given the survey query values to output a final answer. We have two main experimental setups. The first are performed using query templates. These have been mostly performed using the Texas Public Use data files, which are a set of inpatient medical files gathered from hospitals across Texas. These query templates are just gathered from papers on Texas files or just similar data sets that have commonly used queries in studies, such as how many people are above a certain age or how many people of this sex have had this diagnosis. So things that can be easily adapted to any target. The second set of experiments we performed were a case study using an actual medical study performed using HCUP-NAS data, which is a similar inpatient data file set that has been conducted across the country rather than just in Texas. The reason we performed these attacks on an actual medical study was to ensure we had the most realistic setup because we were attacking a real study. This way we can ensure that our queries are queries that are actually used in the world and that an adversary may be actually able to attack. It is quite easy to perform membership inference when you can choose any queries you want, but to get a realistic idea, we have to choose less than ideal ones. Before we get into the actual results, I do want to mention the main metric we use to determine attack success in this paper is advantage, which is simply accuracy over 50% remapped to the 0 to 1 range. So for instance, a 75% accuracy equals a 50% advantage. To a lesser extent, we also usually call them precision. These are mainly within the focus of query filtering and inclusion frequency, which we'll talk about later. Two of the most important factors we found in our experiments were the number of queries and the sample size, and this was across all of our experiments. The more queries you have and the smaller your sample size, the more powerful the attack, because in both of these scenarios, the influence of any single one target is maximized. When you have too few queries or too big of a sample size to detect the influence of a target, the membership inference does not succeed. In our experiments, the in and out distributions used in the likelihood ratio attack and the sample query values used in the machine learning attack are all generated from the auxiliary dataset. What we found in many of our experiments was that the auxiliary data set distributions did not actually match the distributions from the actual survey data set. In this case, the survey query result was more or less impossible under either the out or the in distributions from the auxiliary data set. This actually confused the attack because it wasn't giving any useful information, because whether the target was in or out, it didn't matter. It didn't fit in either distribution. For this reason, if we could detect it, we removed queries where the survey query result did not fit in either distribution, and this resulted in an overall advantage increase for all of our attacks. Especially when the auxiliary difference is greater between the auxiliary dataset and the target survey dataset. For instance, when there's a 1-year difference, you get about a 15% advantage increase, whereas for a 6-year difference, you get a 30% advantage increase. We also experimented with inclusion frequency. When you're performing experiments on membership inference, you have to perform a number of experiments with a target, some of which include the target and some of which do not include the target. In most membership inference papers and in many of our experiments, this ratio is about 50%. 50% of the attacks include the target, 50% do not. In reality, though, this number is much likely to be lower. There's usually a much smaller chance than 50% that the target is actually part of the survey you are trying to attack. For this reason, we tried experiments with the inclusion frequency at 10% and 1%. In these cases, we found that the maximum precision possible is much lower than the 50%, and even with changing the thresholds, it is never possible to get back to that highest precision, largely due to the fact that the false positive rate is so high compared to the number of true positives. As you can see here, a 50% inclusion rate gives us about a 99 advantage, 0.99 precision, whereas a 1% only gives us 0.28. And this is only possible with query filtering, as without query filtering, the 0.28 drops even lower down to 0.08. Either way, though, this should show that inclusion frequency is an extremely important factor in the power of membership inference and should be considered in further research. This brings us to a case study. Our case study examines the paper Racial Disparities in PAD-Related Amputation Rates Among Native Americans and Non-Hispanic Whites, an HCUP analysis. This is an actual medical study, published in a journal, that examines the relationship between race and the use of amputation to treat PAD, or peripheral artery disease-related health issues. This is an important issue because amputation is a less than ideal treatment for these issues. There are other procedures that do not result in the loss of limbs, and ideally should be performed if at all possible. This paper examines this relationship and actually finds that in the western region of the United States, hospitals do perform amputation on Native American patients more often than non-Hispanic whites. They do not know exactly why this is the case, whether it's due to discrimination or political issues or stuff like that, but they do find that it is the case. Now, being inferred in this data set could be damaging for people, obviously because their health history is being revealed, but could also be damaging for hospitals and doctors because it could be inferred that they are potentially guilty of discrimination, which could result in a massive loss of trust and possibly monetary value. We perform membership inference attacks using queries directly from the paper on the data set that is used in the paper, HCUP-NAS, and then use an auxiliary data set that is a year of HCUP-NAS that is not included in the paper. This gives us, we feel, a very realistic attack scenario because we're using an actual paper and data sets used in the paper. One important result we got from our case study was the difference in vulnerability among targets. For instance, we were only able to focus on Native American targets because the non-Hispanic white group was simply too large to attack. They had approximately 10,000 to 100,000 patients per year, which the influence of any one target is simply washed out in sampling and noise. On the other hand, the Native Americans had about 100 to 1,000 patients per year, which is a theoretically attackable size. But we found that even in this, the most vulnerable groups, there's a significant difference in vulnerability between targets. The most vulnerable has a significant risk of over 0.2 advantage, while the least vulnerable has almost no chance of being inferred. We also found that since the attack is overall weaker in this situation, the influence of inclusion frequency was much more significant. At low inclusion frequencies, the precision is almost zero, and there's almost no chance of identifying any targets. So it is important to consider that in future cases. We also performed novel group membership attacks, where instead of attacking a single target, we attacked a group of people, in this case, hospitals. As far as we know, this is the first time these kind of group attacks have been considered, and we found they represent a serious risk. Due to the increased influence of a hospital compared to a single person, the attack power is greatly increased, and as you can see, many hospitals have a significant risk of being identified. As I mentioned earlier, in this situation, if the hospital is identified as belonging to the group that may have possibly discriminated against Native Americans, this could represent a massive loss of trust and even monetary value for that hospital. For this reason, we believe that these kinds of attacks need to be considered in future research. We also evaluated several defenses against our attacks, namely differential privacy and small count suppression. Differential privacy usually works by adding noise to query values so that the influence of any one target cannot be identified, while small count suppression simply removes any queries with a count below a certain threshold. While both of these defenses do eventually defeat our attack, they come at significant cost to utility. This is largely due to a small sample size, as at high sample sizes, these defenses still provide privacy without the significant hit to utility. But at our small sample sizes, they require almost completely removing the queries in terms of small count suppression, or completely changing the query values in terms of differential privacy, where the noise has to be 80% of the actual query value. At this point, the relationships between any queries are essentially removed, and the data is no longer useful. This brings us to our final conclusions. In this paper, we have considered a realistic adversary and the additional factors and methods they must consider to perform membership inference on realistic targets. For instance, query filtering and considerations for the difference between the auxiliary dataset and the target dataset, inclusion frequency, and possible group and hospital membership inference attacks are all issues that need to be considered to properly evaluate the risk of membership inference. We believe that further papers on this topic should include these and other factors. For more details, read our paper. This has been Luke A. Bauer.